Now let us look at another approach, the energy approach, to formulate the same bar problem in terms of mathematics. So you may recall that there is something called the total potential energy. And this total potential energy has two components. One is the internal strain energy and one is the work potential. Okay. And the work potential is basically negative of the work done by forces, and internal energy is the basically the strain energy or the stress strain couple energy. Now the internal strain energy can be written as 1/2 integral over the volume sigma times strain dV. Okay. And recall that for our system we have A equal to 1, which is constant, which means dV is equal to A dx and is equal to dx. So this volume integral basically becomes a line integral. So we have 1/2 integral from 0 to 1 sigma times strain, and once we use the fact that sigma is equal to E times epsilon and epsilon is equal to U comma x, we eventually end up getting the form for pi internal, the internal energy as 1/2 of du by dx whole squared. Pi external is the work done by the forces. So this is L times U. So this is the work done by L, which is the body force, plus U at 1, which is displacement at 1, times H, which is the tip load. Okay. So the second form of the same bar problem is in terms of the energy. And this essentially is the total potential energy of the system. And you may recall that the function u of x, which minimizes this pi, will be the deformation state of the system. Okay, so that will basically be the deformed configuration. Of course, the question is how to minimize. So this how to minimize this particular object pi with respect to u of x, that we will see later, as it requires something called calculus of variations, which we will learn during the process. Another thing to notice is that the function u of x, which can satisfy this, is not completely free. It will have a restriction that u at 0 should be 0. Which means it will have a restriction that it should satisfy the Dirichlet condition which is applied on the system. And this is also sometimes called the admissibility requirements. Admissibility requirement. One more thing which you may notice is that what is the nature of this object pi? In general, if we say, let's say f of x is equal to sine x, okay, where x is the independent variable and f of x is what we usually call a function. Okay, so this function takes a number as an input, which means it comes from the real line, and it gives another number as an output, which means this is a mapping from the real line to the real line. So objects which take numbers, it can be one number or it can be several numbers. So this can be a function of several variables also. So objects which take numbers as input and give numbers as output are called function. Now you will notice that this pi is a different type of object. This pi takes as an input a function and gives as an output a number. Okay, so it takes a function as an input This function in this case is the deformation profile of the bar, and gives a number as an output, which in this case is the total potential energy of the bar. So objects which take function as an input and give number as an output are called functionals. Okay. And functionals remain at the center stage of all finite element discussion, and we will get into very details of how to use these functionals and in what way they arise. Okay. Now one side note is that using the FEM, we may directly minimize this functional to find out u of x. Okay. And how to do that, again, we will see later. Now let's move on to the third approach of formulating the same problem, which is called the virtual work approach. And you may recall the principle of virtual work, which says the internal virtual work is equal to the external virtual work. Now for our sake, let's in this case consider that sigma is the real stress, which is given by E times du by dx. So E times strain is du by dx, and basically u is the real displacement. And we consider epsilon v as the virtual strain, which is dv by dx, where v is the virtual displacement. Okay. And from your basic mechanics or structural analysis course, you may recall that v of x has to be an admissible virtual displacement, which means it has to respect the geometrical constraints. Okay. So what it means is that wherever u of x is given, in other words, it has a Dirichlet condition, v of x must be equal to 0. If v of x or the virtual displacement field is not 0 wherever the system is constrained, that will be a non-admissible virtual displacement, and that will not work. Okay. So with these, we see that the internal virtual work is integral over volume, the real stress times the virtual strain. Okay. And after manipulations, you can see that it comes out to be this. And the external virtual work is the work done by the real forces with respect to the virtual displacement. So it is L times V integral 0 to 1 plus V at 1 times H. So the governing equation becomes this. So I've just taken the external virtual work also on the left hand side. Okay, so this is the internal virtual work, this is the external virtual work. Okay. Now these admissibility conditions we have just discussed, that wherever u is given, v of x must be 0. Okay. And again I will note that FEM can directly take this form and it can solve it. Okay. There is no need to do anything else. Once we formulate this particular version of a problem, the FEM can directly solve that. Now another question to ask is whether this form is equivalent to the earlier forms. Okay, so if this form is not equivalent to the earlier forms, that will indicate that we are not solving the same problem, although we may think we are solving the same problem. So this is what we will see next.